Okay, so welcome everyone. Let's wait for a couple of more minutes to see if anyone joins. Then we can start. So we are waiting for a couple of more minutes to see if other participants join. Then we will start. Okay, so it appears that we can start. So welcome everyone. This is NOC EE-91 NPTEL tutorial on semiconductor devices and circuits. The course instructor is Professor Sanjeev from IIT Bengaluru. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar here. So as you know, the course duration is of 12 weeks and we go live from 5 to 7 every Sunday. And this should be your 11th week. So we are almost at the closure of the course. Okay. So hopefully you have been studying following the course. So without further ado, let's start. So this is week 11. So today what we will discuss? Today we will discuss some basic device terminal characteristics. Device means I mean to say MOSFET. Terminal characteristics. And also we will see some basic circuits, right? Basic analog circuits and solving techniques. Okay. So if you follow these lectures, you should be able to solve the assignments if you have not tried or attempted it yet. Okay. So let's begin. So regarding the first question, it is asked that consider a MOSFET with subthreshold current given by the equation this. Okay. So what do we mean by subthreshold? First thing. So let's say I have a MOSFET. This is a bulk MOSFET. Okay. There can be other types also. For example, silicon on insulator type, LDMOS. Okay. Other kind of MOSFET structures are also there. So it is simple planar bulk MOSFET. Planar, and but I am showing the body terminal at the bottom for the simplicity. So this would be your oxide. This is your N plus diffused or ion implanted source and drain. So let's say this would be your VD. Let's say this would be your VS. This would be your VB, and this would be your VG. Okay. So what will happen in general for operation condition, that there will be when VG will be greater than your VFB or the flat band voltage. When your VG will be greater than your flat band voltage, so depletion will start to occur. Okay. So and after some time, when the your VG has crossed VTH, there will be some threshold it is called threshold voltage. Then there will be formation of inversion charges. Okay. So if we see the voltage length scale, so let's say this is your VFB, this is let's say your VTH. Okay. So what do we call this region? And this region consists of multiple regions. Okay. What is this region? This region is called generally accumulation. Okay. And this is your VGB scale for the time being. So after accumulation, you will enter into depletion. Okay. Then after depletion, in which region you enter? You enter into weak inversion. Then after weak inversion, you enter into moderate inversion, and post that you get your strong inversion. Okay. So this is the flow where your device will operate. The device will be when you sweep your VG. So what is the condition on your surface potential then? If I draw the same thing, and this is your, instead of VG, let me say this is my surface potential. So mapped to this point, this is somewhat called 2 phi f plus some very small value. Okay. So you have not been introduced to this part, but take it as it is. Some very small, around 150 millivolt kind of thing at room temperature. This would be your surface potential threshold condition. And what is surface potential at VFB corresponding to? It is your 0. Okay. So this region is your accumulation, then your depletion, and then it starts to enter your weak inversion, and then it starts to enter your, it would be somewhere here your 2 phi, it will be in moderate inversion, and then it will be your strong inversion. Okay. So this is how the device will operate. This is in terms of surface potential. This is in terms of your gate voltage. Okay, so this is fine. Okay, so what we have studied so far, that our what is the IDVG characteristics you are familiar with, or we call it transfer characteristics, right? This is VG, let's say this is your ID. So how will this look like? Any comment? This will look like something like this. Okay, if you keep increasing your VD, it will just go like this. This is for your VD1, say this is VD2, this is VD3, and I am assuming my source is 0, so my VDS is equal to VD. Okay, whatever potential I am applying here. Okay, so this is how your IDVG looks like. This much you know, right? So now, can you help me marking the threshold voltage here? So whoever has joined, where would be the threshold voltage in this figure? Sorry?
Sir,
Yeah, please go on. Hello? You are not audible. My question is that where should I mark the threshold voltage? Okay, so your threshold voltage would be somewhere here. Okay, this is your threshold voltage. So what do we mean by this region? This region we called as inversion. Okay, or more precisely strong inversion, and below that, this region, whatever is this side, this we call as subthreshold. So what would be subthreshold in this plot? So subthreshold would be this one. Okay, this would be my subthreshold region. So what do you say that in this plot, it seems like that beyond threshold voltage, your subthreshold current is your drain current is 0. But actually that is not the case. Okay, so to visualize this, what do you do? It is in linear scale. Okay, so you have to see the same plot in the logarithmic scale. So if you plot IDVG in the logarithmic scale, it will show something like this. Okay, it will come something like this, and then fall off. Okay, so again, so here somewhere here would be your threshold voltage. This is your VG, and this is your ID, and this is I am drawing in log scale. Okay, basically 10 log 10 log 10 of this. So what I am plotting is log 10 of ID versus VG. Okay, so you see that this current does not become 0, but it has a non-zero value. So for example, if your this current level, say this current level is around 10 to the power 4 ampere, 10 to the power minus 4 ampere. So it would be how much? It would be, let's say, around your 10 raised to minus 10 ampere. So again, it is not zero. That is the point. But when you see in linear scale, be 10 raised to minus 10, but in linear scale you cannot see, right? So it appears to be zero. So now what happens? In subthreshold region, so by the way, this current is called your off current, okay? And at this point, VDD, let's say, so this current is called your on current, okay? So from this plot, you can see that this is a straight line, right? So your log of ID is proportional to VG, fine? So what will happen? Your log of ID will be, let's say, some constant times VG. So your ID would be what? Equal to some constant times Vg, and that would be on the exponent. Okay, so this you can take as exponential of, this is 10 power, okay? So this you can take as your exponential of some other constant, let's say constant 1 times Vg. You can manipulate this. This is pretty easy, okay? So now what happens? You see, you have some kind of relation ID proportional to exponential of Vg times some constant. So what do you think? What kind of current is this? I mean to say, in MOSFET, in whatever the convention so far we have seen, or this current, you say, let's say half mu n Cox W over L VGS minus VTH whole square. This kind of current is, how did you find this current? Do you remember the process? Which kind of transport you have used? You have used your drift mechanism, right? So for drift mechanism, what do you require? You require, you know that in drift mechanism, current is your Q times carrier concentration times mobility times electric field, right? So you need at least good amount of carriers, free carriers, which will carry your current to be present. But below subthreshold, you know that only you will have depletion charges and very minuscule some inversion charges, very small. So how will in a region of small carrier the carrier moves? In other words, how will minority carrier move in a region of semiconductor? It will move by diffusion, okay? This is a diffusion transport in subthreshold. Or the meaning is that diffusion will dominate, will be the dominant current. So in other sense, you can see that if this is your P type, so, and if I zoom only this portion, so what I am seeing, if I am zooming on this portion, I see that I have a N plus region here, N plus region here, and P region here, right? So it acts like a NPN diode, NPN BJT, bipolar transistor. So in bipolar transistor, you know your collector current is proportional to exponential of VBE over VT, right? So same thing. If you go into the detailed derivation, how this current has come, again this, it is a PN junction forming minority carrier current, and in other junction or the collector based junction the current will be collected. Same thing is happening here. One junction is forming at this place. This is the source and channel junction, and this would be your drain and channel junction. Okay, so diffusion will be the dominant factor. So the purpose of telling this is that this kind of equation for MOSFET current is okay. There is nothing to be scared about. In subthreshold region, this is how it behaves. Okay, and also you see in this region you have a constant slope, right? So if I take derivative of log 10 of ID over derivative of Vg, so I will have some constant. Okay, this constant we call as subthreshold slope. Okay, and also there is another quantity called subthreshold swing, that is nothing but 1 over subthreshold slope, or that means your del Vg over del log 10 ID. This is a very important parameter in case of your digital circuits. Okay, so the steeper the subthreshold slope is, that means you require very small voltage to turn off or turn on the transistor. Okay, so the unit is your generally unit is millivolt per decade. Decade means, what is 1 decade? 1 decade is 10, right? So if you increase ID by a order of 10, so this quantity will increase by a order of 1. Okay, so this is a very important factor, and this is, if you do the derivation or if you have followed the lecture, this quantity is given by your phi t natural log of 10 times C depletion over C aux. Okay, this can be simplified to this. Okay, so this is so far the theory is concerned, we are concerned about. So let us see what is the question. The question is that in a die or in a chip there are 10 raised to 7 transistors. 10 raised to 7 means 10 million transistors, and all are biased at VGS and VDD, where VDD same VGS and VDD, where VDD is 4 volt. Okay, so calculate the ratio when your VGS is changing from this to this. That means they want us to find out, this is, let's say, your ID1, and this would be your, let's say this is your 0.3, this is your 0.5, 0.3 and 0.5. So what will be the ratio of the currents, or ID1 over ID2? So what do we know? We know our ID to be, ID1 to be, this is 10 raised to minus 16, 10 raised to minus 16 exponential VGS1 over 1.5 VT. Okay, so similarly we can write my ID2 minus 16 exponential VGS2 over 1.5 VT. So what would be the ratio? It would be 10 raised to 16 minus 16 will get cancelled. So we will have exponential VGS1 minus VGS2 over 1.5 VT. Okay, so it would be exponential. What is your VGS1? VGS1 is your 0.5. So 0.5 minus 0.3 over 1.5 times 0.0259. So this will give you around 172.06. Okay, So this would be your correct answer. Okay. So any issue regarding this?
No, sir.
Okay. So you understood this concept, right? What are the regions and how it will look like? This is nothing but the same plot. Okay. This is the same plot in log scale. Okay. So let's move on to the next problem. So it is asked that with reference to question 1, what is the total current supplied to the chip at VGS equal to 0.6 volt, right? So VGS equal to 0.6 volt, we are assuming that VGS is less than VTH. Okay, that means we are still in sub-threshold region. And it is mentioned that you need to find out your ID total. ID total to the chip. That means you have 10 to the power 7 transistors times ID of one transistor, right? Why? Because you will have the transistor connected like this, right? So like this, you will have a, let's say this is your transistor number 1, 2, and then it is your transistor number 10 raised to 7. So you need to, this is the input total current. So what happens? This branch there will be current, this branch there will be current. So all current will add up if you put KCL in this node. Okay. So we need to find out this ID total. This would be this ID times the entire the number of total transistors. Okay. So it will be 10 to the power 7 minus 16 times what? It was exponential VGS over 1.5 VT milliampere. So it would be 10 raised to minus 9 times exponential 0.6 over 1.5 times 0.0259. Okay, milliampere. So how much is it coming? 0.6 over 1.5 divide 0.0259, shift exponential of that times 10 raised to minus 9. So it is coming out to be 5.09 into 10 raised to minus 3 milliampere. So it would be how much? 5.09 microampere. Okay. So from the option, this will be right, or 5.1 microampere. Okay. Okay. So again, in reference to question 1, calculate the total power dissipated in the chip at VGS equal to 0.6 volt. Okay. So this is your one MOSFET. If you can calculate power of one MOSFET, you just need to multiply it with 10 raised to 7, right? So now tell me what will be the power in this case? What will be the power required for this MOSFET? This ID, you know, this 5.1 microampere, 5.1 into 10 raised to minus 7, because it was, the earlier one was for 10 raised to 7 transistors. And you have a bias here. What is that bias? Let's say some resistance. And what is that bias? Bias is 0.6 volt. And what is the bias on this? D, drain terminal. This is D, this is G, this is S. What is the bias on this terminal? 4 volt, right? If I am not wrong, VDD is 4 volt. So can you tell me what would be the power of this transistor? Or what would be the power dissipated through this transistor? Yeah, Parth, can you try to attempt? Am I audible?
Yes, sir.
Yeah. Can you try that? What would be the power dissipated through the transistor? It's a very important concept what I am going to discuss just now. So please try at least that how should I compute the power? What is power dissipated, by the way?
Sir, VI.
Power dissipated is VI, right?
Yes, sir.
So you know your I. So what will be V here? Which V
VDD.
should I consider? Why not this VGS, VG? Let's say VGG. Why not VGG?
Sir, output is from VDD.
But there is also a voltage source. Why I am not considering that voltage source, VGG.
Yes.
This also should
Sir,
be considered, right?
some voltage drop will be there from VGG to VD.
No, no, no. Suppose you have a system here or network here. Okay, this is your one terminal. This is your another terminal. Okay, let's say this is your G. This is your D. So some current is pumping here, ID, and this is some VD. So what will be the power? You know about passive sign convention? Have you heard of it? If this is your VD, if this is your V and the current flowing is I, so what is the power dissipated? Is VI, right?
Yes, sir.
So now think it in this direction that this is some kind of element. You do not know what is the MOSFET, you just have the access of the terminals. Let's say this is a black box to you, okay, and you just can see three leads or three your leads, yeah, and you are doing a measurement on the leads. So and you are asked to find out the power dissipated. How will you find out? By the way, what is the current in this through gate terminal?
Zero.
So what will be the power for this gate terminal voltage source? How
Zero.
much power this voltage source should be delivering?
Zero. Zero.
It should be zero, right? So this is the
Yes, sir.
reason why we are not considering the gate voltage and we are considering only the drain voltage. Okay.
Yes, sir.
So these are the same thing, right? As long as you see that uh, your I is 0, so you can just simply remove this. So this does not contribute to any power transfer. Okay. So this voltage source is delivering a power of Vd times Id, and this element is dissipating a power of Vd times Id. Okay. Now this is as per the passive sign convention. Now tell me, if this is a voltage source and some current is flowing in this direction, let's say this is Id and this is Vd, what is the power? First thing, whether power will be dissipated or delivered.
Power will be dissipated
Why?
because positive power.
because
Current is high
sine of
in.
Vi is 0, right? Sine of Vi is positive, right?
Yes, yes, sir.
Generally what happens, your this kind of sources current flows through the other direction. So if you calculate your P according to passive sign convention, this thing is called your passive sign convention. So P is minus V times I, right? This means power delivery, power delivered, and this means power
Absorb.
dissipated or
Yes, sir.
absorbed, right? So in MOSFET, understand this very carefully, that this voltage source is delivering power, but this MOSFET is dissipating power. Okay, so this the power dissipated for individual MOSFET will be P individual would be your VDD times ID. That would be your 4 times 5.1 into 10 raised to minus 7 microwatt. Volt into ampere is your watt, right? So now what would be P total? Will be nothing but it will be multiplied by the number of transistors in the chip, that is 10 raised to 7. So this will be gone. So you will only have 10 raised to minus 7 will be gone, and you will only be living with this. So it would be around your 20 microwatt. Okay, so 20 microwatt is the total power dissipated by the transistors, 10 raised to 7 transistors on the chip. So if in any interview or any question, it is if you are asked a tricky question, that what about the gate terminals power, or if I just simply put my VDD equal to 0, say if VDD is equal to 0, then your total power dissipated would be total power dissipated would be 0. Okay, because your gate terminal does not contribute to any power. Why? Because your gate current is 0. Why gate current is 0 under DC condition? Yeah, that is a good question. Why gate current should be 0? Can you unmute and
Sir,
try to attend?
insulator, silicon dioxide is there. So from insulator, no current will pass.
Okay. Another way, that what does it see? It sees a capacitance, right?
Yes, sir.
And if you have some DC source, so what will be the current? Your voltage over
Impedance is
impedance, right?
infinite. Yes,
Exactly.
sir.
Impedance is your infinite. Okay. So you can think it this way also. Okay. So let's move forward to the next part. So it is asked that which of the following statements are true? The interface states affect the subthreshold swing of the MOSFET due to presence of additional capacitance. CV characteristics curve of a MOSFET shifts left right. Trap charge no effect on CV characteristics, and charges present has a effect on threshold voltage. Okay. So first thing, what do you know? VFB is phi ms minus Q oxide over C oxide. Okay. So if Q oxide is not equal to 0, so VFB will change. Whatever threshold voltage, VTH equals to VFB plus 2 phi f plus gamma root over 2 phi f. So if this changes, VTH will also change. So VTH will also change. So charges present at the oxide semiconductor interface has strong effect on threshold voltage. This is true. The interface states affect the subthreshold. Okay, let us go to that after some time. The CV characteristics of the curve shifts left right. So if your VFB and suppose this is your CV characteristics, okay. So this point will be your VFB and somewhere around this point you will have your VTH. So if your VFB changes, let's say this side, or VFB goes down, so your VTH will also go down. So now your plot will be somewhat like this. So your entire CV plot has shifted. Similarly, when VFB increases, the plot will be shifting rightwards. Okay. So this also is right. True. Presence of trap charges has no effect on CV characteristics of the MOSFET. This is wrong because this is true. And the last part is that the interface states affect the subthreshold swing of a MOSFET due to presence of an additional capacitance. So what is your subthreshold swing? It is your phi t ln10 times 1 plus C depletion over C ox. If you do the field line derivation, a simple derivation, it is given in the lecture also, that if you have some positive charges here, okay, so this will add a capacitance CIT in case of this subthreshold expression. So if we incorporate oxide trap charges, then your SS becomes phi t natural log of 10 times 1 plus C depletion plus CIT over C oxide. So your SS will also change. Okay. What happens is that suppose this is your VG. So to see SS, what should be my y axis? Yeah, can you unmute and tell me? To see SS to plot SS, what should be my y axis? Yeah, Parth. As I have mentioned that it should be log scale, okay, log ID. So you will have some characteristics like this, okay. And let me tell you another interesting thing. If you actually plot, it will go up. After this would be somewhere around VFB, and this would be your around VTH, and this is for short channel MOSFETs, and this happens in accumulation region and high VD, okay, high VD and accumulation. This effect is called your GIDL, or gate induced drain leakage. Okay, you can read it more online, or if you are interested, you can email me. I will send you some documents, okay, that how this current derives. It derives at the gate to drain overlap region. Those higher order effects you are not taught in this course, but ever if you see this kind of plot, that log id versus vg, and there is some spike in the deep accumulation region, so or the increase in accumulation, so you will feel that that is due to your gate induced drain leakage, and by that you immediately can tell that your device is a short channel device, okay. So if your this is uh, without traps, let's say without without interface traps. Now if you have interface traps, your SS will be somewhat like this, okay. So it will shift. These are your non-idealities, idealities, or you can say these are real device effects. So whenever you do device modeling, so these kind of effects become very important, okay. So you need to take care of this kind of stuffs also in your device model. These are the realistic model, okay. And in this context, let me put a comment that the equation you see, right, mu n cox w by l, vgs minus vth over vds minus vds square over 2. This we will never find in any actual simulator models, okay. You take your spice, p spice, h spice, cadence vector, anything, this will not be there in any of the models, okay. Never you will find this. It will be much more complicated. Why it will be complicated? To take care this kind of small real device effects, okay. But again, these kind of equations are very important. So you would ask me that why do we use these equations? These equations are very important for the first order hand calculations, okay. Okay, so let's move on. Okay, so it is mentioned that constant voltage scaling is applied to a MOSFET with scaling factor of this. As the MOSFET features are scaled down, the current of the MOSFET will increase or decrease how much. So first thing is that we heard this term for the first time, that is scaling. So what is scaling? Scaling means reduction in dimensions of the device. That means your W, L, TOX, XDEP, XJ, etc. Okay. So why do we need scaling? We need scaling because of high chip density. If you have one transistor, you can do only some operations, okay, very few basic operations. But if you have multiple transistors, if you have ever seen an AND gate or a CMOS AND gate design or an inverter or NOT gate design, you would see that a CMOS, your inverter would be, you can make it with two gates, right? One PMOS, one NMOS. This would be your input, this would be your output. So now if you want to make some AND gate or something like that, you need multiple transistors. And to AND or not, these are very simple operations. To do multiple higher order operations like your microprocessor stuffs, you need thousands, even millions of transistors, okay? But again, you need those millions of transistors in a portable device like, let's say, your electronic calculator or your mobile phones. The dimension should be very small. So to do high sophisticated stuffs, you need higher chip density. So that's why in a given area, number of transistors in a given area, given chip area, you want it to increase, okay? And also if you want it to increase, you do not want your other factors to degrade the overall performance, okay? So there is a very classic paper of 1974, Dennard and his team. You will find it in IEEE Journal of Solid State Society. Okay, so this I will the Journal of JSSCC. I think it is something like that, circuit something. So I will share this paper in the YouTube link. So this is the actually mother paper for all the scaling theory. Okay. So they actually for the first time proposed how should we go about thinking on the thinking about the scaling. So based upon this paper, you will find out there are multiple scalings. Okay. The very famous one is your constant electric field scaling. Then you would find out your constant voltage scaling. And but what actually later on has been followed is a combination of the above two that we call as hybrid scaling. Okay. And much more detail, I think Professor Sanjeev has explained in the lectures. Okay. So here the motto is to keep electric field constant. Here the motto is to keep voltage constant. Okay. And here is a mix and match. So in this particular question, we will discuss about the constant voltage scaling. Okay. So what do constant voltage scaling mean? Meaning your that L will be scaled by a factor of K, W will be scaled by a factor of K, TOC should be scaled by a factor of K, and your voltages would be remain same. Voltages remains constant. So now the question is that how will my current scale down or scale up? So your current is what? Half mu n Cox W by L VGS minus VTH whole square. Okay. So your what have scaled? So now let me write down. I scaled is equal to half. Mu n is a device constant. Cox is your Eox over Tox over K. This is W over K and L over K. And this is VGS minus VTH whole square. Voltages are not scaled because we are using a constant voltage scaling. So this K will get cancelled, but this K remains. So you will have K times half mu n Cox W over L. This Eox over Tox I am writing again as Cox and VGS minus VTH whole square. So this part is your I So K times I. Okay. So in constant voltage scaling, your current will increase by a factor of K. So if K is 5, so current increases by a factor of 5. Okay. So this is how you go about solving this kind of problems.
Sir,
Yeah.
sir, when we decrease thickness, then current will tunnel.
Current will tunnel. Yeah,
Uh,
yeah, obviously. See, right. Very, very, very good point. So, okay, just let me explain it in detail. So, what happened actually around your 1960s, when the first time your transistors are coming about, what was your TOX? Any idea?
no, sir.
It was around 100 nanometer. Okay. So, and there is a thing that Moore's law. You have heard of Moore's law?
Yes, sir.
What is Moore's law?
Every some year transistor
Every 1.8 year, number of transistors in
doubles.
a given area doubles, right? Okay. So what does that mean? Your WL needs to be half, right? 0.5 WL scaled needs to be half WL, what was earlier 1.8 years earlier. So what your WL scaled is what? W by K times your L by K would be your what? 0.5 times WL. So this, if you can cancel, your 1 over K square will be around 0.5. So your 1 over K or the scaling would be around 0.7, right? Because 0.7 times 0.7 is 0.49, almost equivalent to, right? So generally in every 1.8 years, your device dimensions are scaling down by a factor of 0.7. So that means if 1960 100 nanometer were used, after some time, let's say 1962, these are just examples, okay, not exact. So after then, what would be your device TOX? TOX would be your 70 nanometer. Then after, let's say 1964, your TOX would be how much? 7 times 7, that means your 49 nanometer, right? So this way it will come down, okay? So do you have any idea what is the current device dimension?
3 nanometer.
No, no, that is the minimum scale length, right? Minimum feature length, 3 nanometer. What is the oxide we can afford? Oxide we can afford up to zero point 0.7 to zero point 0.8 nanometer, okay? These are the state of the art. State of the art means very current, what is going on right now in the research. 0.7 to zero point 0.8 nanometer TOX is there. But if you reduce it further, then tunneling start to take picture, okay? That is what you are concerned about. But what we needed EOX by TOX, EOX by TOX to move up by a factor of K, right? Can you unmute?
Yes, sir.
So EOX by TOX by a factor of K. So far we have assumed that my EOX is constant, right?
Yes, sir.
Now suppose instead of increasing TOX, how can I increase EOX?
The Riox is the metal characteristic, so
No,
we have to
metal,
change
how,
the
what,
metal.
no, it will not be metal, right? EOX.
Metal is a material.
So what is the material? It is ER times E naught.
Yes, sir.
So ER you can improve? Silicon dioxide. So far we are discussing about silicon dioxide as oxide, right?
Yes, sir.
So silicon dioxide has a dielectric constant of or ER of 3.9, right? We have been discussing this so far.
Yes, sir.
So what people have come up that let us put a high K dielectric. This is also called K or dielectric constant. So high K dielectric. Okay. So they have started to use HFO2 or hafnium dioxide. Okay. So this has a ER of 25 to 26. So you see, you do not need to scale your TOX down further. You can stop at a time, and whenever you are hit the tunneling limit, you can use higher order higher order dielectric constant materials, okay, or high K dielectrics. This is one way to accommodate that, okay. But what is the issue with that? You got your point, right?
Yes,
You are
sir.
absolutely right. The tunneling will be there, but due to if tunneling, we want to reduce the tunneling, we can obviously use a high EOX device. That will also give me the same performance, isn't it?
Yes, sir.
But what happens? It is hafnium dioxide and this is silicon. Okay, so this interface is very poor. So what people have come up with, they use this kind of structure. They use hafnium dioxide for the majority part of the oxide, because you see your tunneling does not depend upon your ER. It depends upon only TOX, right?
Yes, sir.
So if you take your hafnium dioxide, you can increase your TOX.
Yes, sir.
So they put a very small thin layer of SiO2 and then they use a silicon substrate. So that what happens, your transport at the silicon and silicon dioxide interface remains intact. Let me, you have to participate, okay, in this discussion. Otherwise, I am not sure whether you are getting the stuffs or not, because this is not in the coursework. This is, I am telling something outside of the course, okay? Just because you have asked it. Suppose you have a interface. Where does the electrons, this earlier, what was that? This is silicon dioxide and this was silicon, okay?
Yes, sir.
So there were, these are the inversion layer electrons
Yes, sir.
and these are my N plus drain VD and these are my, let's say, N plus source, okay? So electron will move in this region only,
Yes, sir.
near to the surface.
Yes, sir.
So if electron moves near to the surface, there will be certain discontinuity in the interface, because these are not the same material.
Yes, sir.
Some roughness, surface roughness.
Yes,
So
sir.
this will lead to your surface roughness scattering. Remember, I
Yes,
have
sir.
discussed this in case of scattering, that there in MOSFET devices, surface roughness scattering play a major role.
Yes, sir.
Surface roughness scattering, and what parameter it will affect?
Flow of electron.
What parameter?
ID. Drain current.
Drain current is your half mu n C EOX over TOX W over L VGS minus VTH whole square. Which parameter among
Mu
these?
mu n.
Exactly,
Mobility.
right? Mu n will get affected. So you see, when we discuss about the first order model, we take these all constants, but these are not actually constants, okay? This changes with the fabrication process and how you are interplaying with them. Suppose in case of silicon dioxide, I am using hafnium dioxide. This roughness will be much more because these are completely two different kind of materials.
Yes, sir.
So this will give me, this part will improve, right? But this will get hit, mobility.
Yes, sir.
So what people have come up with, they have come up with, let's do one thing. Let this be my surface. Here my electrons will be moving from source to drain. And let us put a very small layer of silicon dioxide. This is my SiO2. And other part, I will compensate with HFO2. So what happens? Your surface remains intact.
Yes, sir.
And what is the gain you are getting? That your TOX, or it is called EOT, effective oxide thickness, oxide thickness is not, has not hit the order where your tunneling will take place.
Yes, sir.
So what did you achieve? What did we achieve using this configuration? Or it is called high K dielectric. This one we achieved that mu n remains fairly intact. And what is the other thing we have achieved? That TOX effective
Reduce
will
it.
not hit the tunneling limit.
Yes, sir.
So this is one way. Okay, there are multiple ways. In which course you have enrolled? You are undergraduate or postgraduate student?
Undergraduate.
Okay. In which year you are now?
Sir, completed.
Okay, you are preparing for GATE.
Yet, yes, sir.
Okay.
This year
So
completed BTech.
after that you are planning to go for higher studies or job?
Higher studies.
Okay. Good. Very good. So if you are planning to go for higher studies, okay, then you will pursue your MTech. Most probably, if you are interested in VLSI and microelectronics, okay. So in those courses, you will get to know much more about the advanced structure. I am not sure whether MTech you will get to know, but if you do research work in MTech or your MS, so you will get to know much more advanced level of devices, okay, like your SY MOSFETs, FinFETs, then your HEMTs, high electron mobility transistors and all. So there these concepts come very handy, okay. So the concept remains same, okay. This equation will never change. Though this is not the complete equation, this concept will never change. You just, with the understanding you have developed in this course, it will be very helpful for you to get grasp of the heavier concepts, okay. So
Yes, sir.
hang on till then. You prepare focusing on the gate only, as I will suggest you that when you get yourself enrolled in any IITs, there you will get to learn much more in depth about these kind of subjects, okay.
Yes, sir.
So but your observation was very good that if we reduce the oxide, tunneling will happen, okay. To prevent that, this is one mechanism, one of the many mechanisms that high K oxides you can use, but it has its other effects also, and that is also mitigated by other kind of methodologies. So I can discuss some of them, but this is not the right place, okay.
Yes, sir.
Okay, so let's move on. It is mentioned that uh, consider transistor following parameters: oxide thickness this, acceptor concentration this, operating voltage this. If constant field scaling is applied with the scaling factor of this, channel length and channel width for the scaled device would be respectively. So again, irrespective of constant electric field or constant voltage, my device dimension will be scaled down by a factor of k. So L scaled will be L over k, and my W scaled will be W over k. L was 1 micrometer over 1.43. It will give me 0.7 micrometer. That one I have discussed. Okay. This is the factor would be 1.43, which will give you 1 over 1.43 is 0.7. And why 0.7? Because of this fellow's prediction, Moore's law. Okay. So this is your W scale would be then what? 10 micrometer over 1.43. That is your 7 micrometer. Okay. So 0.7 micrometer and 7 micrometer. This would be your right answer. Can you tell me what would be the scaling on NA? How will NA get scaled? Should we scale it or not? Your all device dimensions has to be scaled. Okay. W you have scaled, L you have scaled, TOX you have scaled. But again, there is another thing which you should also consider, right? Your X depletion. What is your X depletion? Why did I draw a MOSFET? This is your X depletion, okay? So X depletion is also needed to be scaled. So what is your X depletion? X depletion is your 2 epsilon s times psi s over QNA. Okay. And what is my constant field? E has to be constant. That means my voltage over some length has to be, if my length is reduced, V has to be reduced by K, L has to be reduced by K. So in constant field scaling, all device dimensions scaled down by 1 over K, all voltages are scaled down by 1 over K. Okay. So now you see you need X dep over K, right? So how will you find that? You have your 2 epsilon s times psi s over K because it is a voltage, and you have Q. So your NA you need to do up or down. NA you need to increase, right? Then it will become root over 1 over K square times 2 epsilon s psi s over QNA. This factor square root will give you a factor of 1 over K, this one. Okay. So in constant field scaling, your NA will be up by a factor of K. Remember this point. Generally, when we do scaling, we tend to remove the X depth portion, but your X depth is also a device dimension. Device dimension means a device characteristic length, you may say. That also needs to be scaled down. Okay. Otherwise, what will happen? Your voltage is scaled down, but your length is not scaled down. So electric field will get scaled down. So it will never remain a constant electric field scaling. Okay. So moving on to the next problem. What will be the oxide thickness for a scale device given in question 9? It is question, okay, it is question 6. So oxide thickness, it was mentioned 25 nanometer, right? So Tox is 25 nanometer. So your Tox scale will be 25 over 1.43 nanometer. That is your 17.5 nanometer. Okay, because 25 into 0.7, 175 by 100, 175 by 10, so 17.5. So none of this will be the right answer. Okay, so at this place I will stop discussing about the circuits, stop discussing about the devices. Okay, now I will move on to circuits. Okay, is that fine? Any question till now?
No, sir.
Okay, so let's move on to the circuits. Okay, this will be helpful for you to solve the assignments of this week. So first let me ask you, how much familiar are you with the small signal analysis? Means if I what is the small signal of this? How should I, what is the small signal of this transistor? You have done this, right? This, and then there is a current source, then there is a resistance.
Yes, sir.
You have been taught like this, okay? GM, VGS, and this is your VGS, right? This is
Yes,
your
sir.
G, this is your D, this is your S. But what happens actually, you have to make this kind of circuit every time, and you will not get any insight out of it. Most of the times, the equation, it may appear to use a scary stuff, okay? So, are you comfortable using this, solving this kind of circuits?
Yes, sir.
Okay, but I will tell you a further simplified version, okay? So, let me just solve this problem only, then I will discuss parallelly. So, this is a circuit, okay? So, how will be the small signal equivalent? What I will do, I will keep the MOSFET symbol same, okay? Instead of turning it around and doing like this, I will keep the MOSFET symbol same. And what I will do, and in small signal, what will be your current source? You have a V in here, right? And you have a RS here. And you have some output impedance. Output impedance you will have, okay, let's not use red. Output impedance you will have between this. This is, let's say, GDS or RDS, whatever it is. GDS would be your conductance, RDS would be 1 over GDS, okay? And what should be the potential at this terminal or drain terminal? This is V out, right? And what about this stuff? Where will this go in the small signal? Please unmute and tell me.
That is short circuit.
Why? Just telling won't be enough. You need to give reason.
In a small signal, we only see this AC. DC should be uh, ignored.
Okay, then
Then VDD is DC, so
see, there is the
it,
lack of concept. Okay, that is what I am telling you. That is why these tutorial sessions are there. Suppose you have a current source. Keep yourself unmuted. Okay. Suppose there is a current source. This is your VDD. at this point is your V out, okay? Some other place you are giving some V in signal, so this voltage will be fluctuating at V out or this node due to small signal.
Yes, sir.
Now, what is a current source?
Which does not change with voltage, independent of it should be constant.
So independent of what is the voltage at this node, because this is constant, so the voltage difference change will be depending upon this part, this change.
Yes, sir.
So whatever change due to small signal will be there. What will be my current? Current will keep remain I0, right?
Yes, sir.
So now if you take the resistance of this current source, let's say R of I0. If you take I0 is subscript, okay? So if you take this resistance, what will happen? It will be delta of, let's say this is your Vx, let's say delta of Vx over delta of I0.
Yes, sir.
So what is your delta Vx? Is this variation? Let's say this is delta V, and what is your delta I0?
0.
So what is your impedance?
Infinite.
So what is an infinite resistance means?
Open circuit.
So you told short circuit, right?
Yes, sir. Open circuit.
Do you see why it will be open circuit? Once you understand that if you see a current source, ideal current source, then you will never forget that it is an open circuit in small signal sense.
Yes, sir.
So far you have just remembered that it should be short circuited, but it is not the case once you know the logic behind it. Okay, so for simplicity, let me draw it like this. This is your V out, and what will be this? This will be open circuit, right?
Yes, sir.
Can you visualize this circuit from this to this? These are the same circuit in small signal sense.
Yes, sir.
Okay, so if that is fine with you, now let me remove the open circuit part because there will be no current flowing through.
Yes, sir.
Okay, now understand this very carefully. This is a node. There will be certain potential developed. Let me call it Vx. Okay.
Yes, sir.
So what is the current through this transistor in small signal?
Vx times GDS.
GDS, why it will be GDS? This is the stuff, right? This part you are familiar with. So between drain to source of the MOSFET, what is the current? It is GM in times
VGS.
VGS, right?
Yes, sir.
So what it should be? This current? This current should be GM times V in minus Vx.
Yes, sir.
Do you see? If you cannot understand, please tell me right now.
Yes, sir.
It is fine with you?
Yes, sir.
Okay. So if that is the case, can you tell me what is the current flowing out of this transistor?
Same current.
Which current?
GM times V in minus Vx.
Why? Why?
No, drop also there.
Okay, okay, okay.
RS.
There is an issue in the concept. Okay, just let me blow it up and then discuss. This much you are fine.
Yes, sir.
Now you see, this is the current coming here. Okay. Uh, where is that? Okay. This current is coming in this place. Now
Yes, sir.
it has what path to go? It can go
Uh,
this way and it can go this way.
yes, sir. Sir, before that,
This
will
current, it
you
will
explain about GDS?
GDS. Okay. GDS is nothing but due to channel length modulation, there will be a resistance, right? Output resistance.
Yes, sir.
This stuff you draw, right?
Yes, sir.
This is between drain and source. That is your RDS. GDS is
Yes,
nothing but your 1 over RDS.
yes, sir.
Okay.
Yes, sir.
So is that fine?
Yes, sir.
So now you see at this place GM. Okay, just let me erase this part and write it clearly. This should be your GM times V in minus Vx. This is clear, right?
Yes,
Now
sir.
this current is coming at this node. It is seeing a node. So it can go here or it can flow out. Okay?
Yes, sir.
Which direction it will go? How to see that? Then what you will take, you consider that this is a box, okay? What is the current coming in? From this to this node?
GM into
No,
VGS.
no. This current outside the box. Suppose this box you are not aware of that there is such box is there. What is the current coming in? Okay, just let me tell you in this way. This is V out.
Yes, sir.
This is what voltage? What is the voltage at this node? This is also V out, right?
Yes, sir.
So what is the current here?
Same potential, no current.
Zero current.
Yes, sir.
So what will be the current coming out of this node?
Zero current.
Zero current will come out, right?
Yes, sir.
Why zero current will come out? Because it is a
ACL.
box.
Yes,
It
sir.
is whatever is coming in, it should go out.
Yes,
Okay.
sir.
So what happens? That entire current will be diverted through GDS only. This
Yes, sir.
entire current will divert it through GDS only. Okay.
Yes, sir.
And it will then create a potential at this point or this point. That means your V out would be nothing but minus GDS, or let's say it is RDS times your GM V in minus Vx.
Yes, sir.
And what is your Vx? If there is zero current, then if there is zero current, that means this and these are short. This is grounded actually.
Yes, sir.
Okay. So this is one way to see the circuit. Other way, you can obviously do the maths. Let me do the maths also for you. So what did we have? We have a MOSFET. We had a resistance. We had a, let's say, RDS, and we need to find out V out over V in, right? So what will we assume? Let me just zoom it. So we'll assume some potential here Vx, okay, and this is your Rs, let's say. So this would be what? Gm Vgs. So Gm Vgs is what? Vgs is your V in minus Vx plus what is there will be certain current flow in this branch. If I do the pure maths, this is my V out, this is my Vx. So current in this branch would be V out minus Vx over RDS. That will be equal to this current out. If I apply KCL at this node, so that should be what? Vx minus 0 over Rs. Okay.
Yes, sir.
And this current is 0. So this out current will also be 0. And from that place, you consider your Vx is equal to 0. You put your Vx 0 here. So this entire quantity becomes 0. So you are left with Gm times, and this is also 0. Gm times V in is equal to minus V out times RDS. So your V out over V in would be minus Gm times RDS. What is your Gm given? Gm given is 1 millisiemens and output conductance is 10 kilo ohm. So minus 1 millisiemens times 10 kilo ohm. So it would be minus 10. Okay. So your gain is minus 10. Magnitude they have asked, so 10 would be the right answer. So your gain does not depend upon this Rs, because in small signal sense this terminal becomes a ground. Okay.
Yes, sir.
So this is an easier way to solve the circuit. Once you try to do it multiple times or multiple problems, so you will not be using, do not use this for quick calculation. Okay.
Sir, if input is from V in, if input is from gate or source, source or drain,
Okay.
it's common gate, yeah, common drain, then our RS will be relevant there.
Okay. Okay. Let's take your question. So this is as far as the above problem goes. Okay. Now
Yes.
question is, what about common gate structure? Okay. This should be your RDS, let's say, and you do not know what is your input and what is your output. Depending upon which potential is higher, you will have that terminal as drain, because MOSFET is a symmetric device, right?
Yes, sir.
So let's say this is your input D, this is source. So your signal will travel from this,
Yes, sir.
and some portion of the signal will travel from this also.
Yes, sir.
So what is the issue?
No, there is RDS. Uh,
Okay.
So we neglected that RDS. We said that
Why are you neglected that IDS?
because I is 0 in previous case.
In previous case, where did we neglected that RDS? We have not neglected any RDS. GDS
No,
is
sir,
still there.
no RDS, not RS. Source
RS, okay,
resistance.
okay. No, no. Source resistance in small signal sense, it appears that RS is not present. But in many circuits, RS may be present.
So RS will present, then we have to apply only this circuit only, na KVL.
See. The way to go about the problem is you draw the small signal equivalent, okay?
Yes, sir.
You then take multiple nodes, you will find out the relations itself, that how the currents are flowing. If some currents are to flow through RDS in a particular structure, it will flow. What is the issue in that? For this particular problem, RS is not important. It is not sacrosanct, okay?
Yes, sir.
Similarly, if you go to the next part of the question, that if the value of RS is 3 kilo ohm, magnitude of the small signal voltage gain will be, it will remain same, because my gain formula, we have seen that what is my gain? Minus GM times RDS, it does not at all depend upon RS. So it will remain minus 10 only, irrespective of whatever you take your RS value. Okay.
Yes, sir.
So let me solve multiple problems, then you will feel more comfortable on this. Okay. So now this is another question. Calculate the approximate magnitude of the small signal voltage gain. Okay. How will you do that? First thing is to draw the small signal equivalent. So this is a NMOS. Okay. Let me just write it for clarity, that it is a small signal equivalent. Okay. And then it is a PMOS. This is ground. This is ground. This is your V in. This is your V out. Okay. And what about this? This is a resistance RD. And what should I do to my VDD? VDD should be grounded in small signal.
Yes, sir.
You have confused this VDD grounding with this current source, right? Earlier last time.
Yes, sir.
So this will be ground, but anyhow at this point it will be open circuit. So it doesn't matter whatever is there after the open circuit. Okay.
Yes, sir.
So this small signal equivalent is okay for you?
Yes, sir.
Okay. So they have mentioned it explicitly, ignore body effect and channel length modulation. What does that mean? That means I have that RDS is infinity, right?
Yes, sir.
That means this we can ignore. In both the transistors, RD is not present, okay?
Yes, sir.
So there is a node Vx. What is the current through this? Just make a guess. Whatever you have understood so far, just make a guess. What should be the current? If this has a GM and this has also GM as a transconductance. What will be the current? Come on, this is easy, right? This is a PMOS, right? Am I audible?
Yes, sir.
This is a PMOS, right?
Yes, sir.
So what is the current in a PMOS? GM times VSG.
Yes, sir.
This is my S. This is my G is grounded. So what will be the current? GM times Vx.
Yes, sir.
Okay. And this is a series combination. So this current will also have to be GM Vx.
Yes, sir.
Fine. And in another way, what is this current? This current also, this gate voltage we know, drain voltage, source voltage we know. So what should be this? This should also be GM times V input minus Vx.
Yes, sir.
So GM Vx is equal to GM times V in minus GM times Vx. So what is your Vx? Vx is your V in by 2. Is that okay?
Yes, sir.
If GM is V in by 2, so what is the current flowing? I is equal to GM times Vx, that is GM times V in over 2, right? This current, whatever this current, that's only one current only will be flowing because it is a series combination, right? This current is your GM times V in over 2. So what is this voltage? How will you calculate this voltage? So there is a current flowing outside, right? So your 0, let's take the same direction. There is a current flowing this side. This is also I. So 0 minus V out over RD is equal to I is equal to GM V in over 2. So your V out over V in should be minus GM RD over 2. This is your gain. So your GM is given, RD is given. So your gain would be, magnitude of gain would be 10 by 2, that is 5. Is that clear?
Yes, sir.
So what is the crux of the problem? Crux of the problem is for you to see that series contraption, in a series connection, only a single current will flow. That is the definition of the series circuit, right?
Yes, sir.
So the current flowing through the PMOS will be the same flowing through the NMOS, will be the same flowing through the RD. Okay. So
Yes,
you
sir.
see, if you can solve it in this manner, it will be very easy for you to solve quickly. Okay. So let's move on to the next problem. This problem I will discuss later because it will break the rhythm. Okay. So let's discuss this. In a small signal resistance kilo ohm of an N channel MOSFET shown in the figure below, a bias point this, transconductance this. What is the channel length modulation? Ignore the channel length modulation effect. Okay. So what is happening actually? Your gate and drain are connected. Okay. This is your VB. This is ID. This is MOSFET and this is this. What is this connection, by the way? This connection is called a diode connected MOSFET. Okay. A diode connected MOSFET. Now, what is a special feature? It always remains in saturation. Can you please comment on this? Why I have written this?
Vg is always equal to VDD.
Vg, no, not, there is nothing to do with VDD. What is the condition on saturation? First tell me what is the condition on saturation? What is the
VD minus
saturation condition?
V.
VDS has to be greater than VGS minus VTH, right?
Yes,
So if your VGS is equal to VDS, so you can write your VGS greater than VGS minus VTH. This condition is always true
yes,
as long as your VTH is greater than 0.
yes,
So this condition will always be satisfied. Okay. So that is why it remains always in saturation. Remember this point. This is a diode connected MOSFET. So now if you write the current relation, what will be the current relation in saturation? What is the diode current relation? Half mu n Cox W over L VGS minus VTH whole square, isn't it?
yes,
So what is your ID? 1 over 2 mu n Cox W over L. What is VGS? VGS is nothing but VB minus VTH whole square. So now you want to find out dVB by dID. So let us calculate dID over dVB first. That is what? 2 will get cancelled. So you will have mu n Cox W over L VB minus VTH. So your dVB over dID would be what? 1 over mu n Cox W by L times VB minus VTH. Okay. So what did they want us to find out? This quantity only they have want us to find out. Okay. So mu n Cox W by L is 40 microampere per volt square. So this is 1 over 40 into 10 raised to minus 6. And what about VB minus VTH? VB is given as 2 volt. And what is your VTH? VTH is 1 volt. So 10 raised to 6 over 40 ohms. So dVB over dID is your 10 cube over 40. This is your 40. This is your 2 minus 1. So how much will it be? And this is kilo ohm, let's say. So this is 1000 over 40 kilo ohm. That will be your 25 kilo ohm. Okay. So what is the, where would you stuck if you were to solve the problem? You will start to realize this equation, because you had two options to go with either linear or with saturation, right? Here you can see that easily, as it is a diode connected, it will always be in saturation. So understanding that remains the crux of the problem. Okay, I think it is pretty simple.
yes, sir.
So moving on to the next problem. So we want to find out the small signal gain of this contraption. Okay, again the same stuff what we do usual. First we make, and also all transistor is no channel length modulation is non-zero, right? So we have to consider GDS, non-zero GDS, okay, or RDS, that for that matter. So let me draw the transistors. And this will be, this is a NMOS. Okay, so this will be coming down here. This is like this, and it is something like this. This is V in. There will be one resistance here. Let's call it R01 or 1 over GDS, same thing. Or let me call it G01. It is easier for me to calculate in terms of conductances. So this is entire rail was VDD. So this will be ground. So there will be a resistance here. This VG will be ground. So this will be your G03. There will also be a G02. Okay, this will be ground. This will be ground. Fine. So first thing that, and this is your V out. Okay. First, let us take this contraption. So what is the impedance looking in? How will you find out that? The way to find out is, you let us copy this. How will you find out?
Norton's equivalent.
No. There are much more simple things. You don't go to those steps. It will take time. Okay. You apply a V test. Okay. And you measure I test. Fine.
Yes,
So if you apply a V test, what will be the current through this? It will be GM what? GM2 times GM2 times V test, right? GM2 times V test will be there, and
yes,
another current will flow through this. That will be your V test. Sorry, your V test over GO2 times V test, and this entire current, this branch current and this branch current is equal to your I test. Okay. So what is your R in? R in is nothing but your V test over I test. That will be equal to your GM2 plus G02. Sorry, it will be 1 over that, right? Did you understand this part?
yes. Sir, by seeing both are in parallel, so we can directly write this.
Once you are very much mature after solving this circuit, then you can do. But I will suggest that till your gate exam is complete, even till in your gate exam also, use this only. Then there will be no, because there may be other loops and other configurations which you will not be able to catch at looking at the instant. Okay, so you may miss something if you use direct formula or by just by looking or inspection. So that stage you will be reaching, but let it be for the latter part of your career or in your MTech. Okay.
Yes, sir.
till your gate exam, I will suggest you to do this way only, because in that way you will not be able to make any mistake. Okay.
Yes, sir.
So this is your, so this entire thing I can simply draw with a resistance, and that resistance will be my, let's say the conductance would be my GM2 plus G02. Okay. Now let us take this contraption. So what will I have? I have a PMOS. This is ground, this is ground, and this is, so I need to find out, looking into this, what is the impedance. Can you tell me what is the impedance directly? Can you unmute and try?
So directly same impedance seen.
What is that?
One is one by GM2 by GOS.
Remember, this is a PMOS. That is gate, it is source. So your VGS is 0 because both are grounded. So no current will be flowing through this because GM times VSG is 0. So
Yes,
you
sir.
are only seeing this resistance. So Rin will be 1 over GO3 only.
Yes, sir.
So why did you tell that it should be GM 1 over GM2 plus GO3?
Sir, I didn't see ground. Gate is grounded.
No, the gate is grounded. This is,
Both
in
are
this case
short
also
circuit.
gate is, in this case also gate is grounded. So what is the difference between this and this? Try to look carefully at the circuits. Okay, this is a NMOS. Okay, so whatever voltage difference between this place, current will be flown due to that region. This is a PMOS. Again, what is your current? If VGS will lead to GM VGS current, right? For NMOS. For PMOS, VSG will lead to GM VSG current for PMOS. Okay. Here your VSG is 0. Here your VSG was not 0. G was 0, but V was V test.
Yes,
Do you see it?
yes, sir.
So this is only GO3 because, because the, what would be this current? This current would be GM VSG, that is 0. That means
Yes,
there is current 0 means what? Open circuit.
yes, sir.
So if it is open, then it would be only GO3,
Yes, sir.
right? So if so, it will be only GO3. So now what is your circuit configuration? Final circuit configuration. You have a V in here. You have a GO1 here. Okay. And you have a, this is your impedances. This you have take grounded. This would be your GO2 plus GM2. This is your GO3. So what would be the gain of this circuit? How will you find out? Again the same method. What is this current? This current is what? This is G, this is S, this is V in. So this current
V
will be
by GO3.
GM into V in, right?
Yes, sir.
if this current is GM into V in, and there is another current also, so GM into V in plus this current V out into GO1 is equal to the total current. Total current would be what? Minus V out into parallel combination of this all. So GM2 plus GO2 plus GO3. So if you solve it, what will you get? You will, let us take V out at one side. V out at one side would be GO1 plus GO2 plus GO3 plus GM2 would be equal to GM times V in. So what is your V out by V in? Minus GM over GO1 plus GO2 plus GO3 plus GM2. This is your gain. So this, do we have an option? Okay, if we take it in terms of R, then V out by V in would be equal to minus GM, and 1 over this parallel combination would be, it is nothing but a parallel combination. So your RO1 parallel RO2 parallel RO3 parallel 1 over GM2. So this will be your gain. Okay, this would be your gain. Which part you did not understand? I know you have not understood this problem. Which part you did not understand? Please tell me.
Understood, but
What is the feeling? Tell me.
it's okay.
It's okay. So you will be able to tackle this kind of problem?
Need some practice.
Need some practice. Exactly. Very good. I appreciate your honesty. That exactly this kind of circuit, see, to see that how, at which node the current is flowing in and flowing out, the entire thing, that for example, uh, this entire stuff is a single combination. So whatever is V out is there, this entire V out will be flowing some a particular resistance. It is a parallel combination, and again the same current is dividing between these two branches. So this needs some practice. Okay, you are absolutely right. What I will suggest you, uh, there is, which book should I suggest you for analog circuits? Cedra Smith is a very good book for practice. Boylsted exercise, then Cedra Smith exercise, and get previous papers. Okay, you solve this in 1 week, you will be able to solve any analog circuits uh, about this BTech level. Okay,
Yes.
so you use these books. These are very good books, and this will also come handy. Okay,
Sir,
so
PDF.
PDF. So okay, I told you to mail me, right?
Yes, sir.
So do that email, I will revert back on that.
Yes, sir.
Okay, so again, this is another problem where it is mentioned that ignoring the channel length modulation, find out the small signal voltage gain. Find out the small signal voltage gain. Okay, so what will you do? We will draw the small signal equivalent. So it is an NMOS, and we need to ignore the channel length modulation, so no RDS will be there. So this will be grounded. This is also grounded, and this is also another NMOS. This kind of connection is known as cascode connection. Okay, not cascade, it is cascode. So this is your V in, so this should be your V out. Okay, so how will you find out this small signal gain? Find out the small signal gain, W by L. Okay, so this is V in. So what is the current flowing in this? GMV in, right?
Yes, sir.
So, and what is the impedance looking upward? Have we seen this kind of phenomena?
Yes, sir.
Here we have seen, right?
Yes, sir.
So what was the impedance looking up? It was GM2 plus GO2. So it would be GM2 plus GO2 times V out, right? So
Yes, sir.
GO2 is 0 because my channel length modulation is not present. So you find that GMV in is equal to minus GM2 times V out.
Yes, sir.
So what is your gain? V out by V in is equal to minus GM2 over GM. What is your GM? Okay, now let me tell it. ID is equal to half mu n Cox W by L VGS minus VTH whole square. Okay,
Yes, sir.
and your GM is mu n Cox W over L VGS minus VTH. Okay, is that okay?
Yes, sir.
So you have your, if you want to find out your, let's start with ID is equals to half, let's say mu n Cox W by L times VGS minus VTH whole square. That means I need to multiply in this side also mu n Cox W by L, because I have taken this also whole square, entire thing whole square. This is your GM. So you have 2 mu n Cox W over L times ID is equal to GM square. So your GM would be equal to square root of 2 times ID times mu n Cox W over L. Why did I do in this form? Because, what do you think? Why did I derive it in this form? Because my ID is constant, okay? Because this is a series contraption, so ID flowing through both the transistor will be constant. So I want my ID to be constant when I replace my other quantities, okay? So you see, if you use this formula V out over V in, you will find out your GM2 over GM. So minus of, what is GM2? GM2 would be root over 2 ID2 mu n Cox W2 by L2 over root over 2 ID1 mu n Cox W1 over L1. So now if your ID is constant, which it is because it is a series contraption, So this term you can cancel it. So your entire thing would be root over W2 by L2 over W1 by L1, and that is your, what is W2 by L2 is nothing but your, this would be 40 by 0.5 and this would be 10 over 0.5. So minus 0.4. So minus 2 would be your gain. Okay. So yeah,
Gm equal to mu n Cux W by L Vg minus Vts this equation.
this equation why cannot we use, right?
No sir, this equation come from where? Yes sir. Okay sir.
Okay. But why
Yes.
did you not use this equation? Because for these two transistors, my this quantity is not same.
Yes sir.
But what is same? ID is same.
ID same.
So that's why we use convert this equation to this form and then use. Okay.
Yes sir.
So this is a very important, this is an very important question which often comes in GATE exams. Okay.
Yes sir.
So please spend more time on this kind of problems. Okay. So moving on to the next problem. Considering this threshold voltage, find the ratio of W1 over W2. Okay. Again, what is the crux? Crux is that it is a series combination. So this current should be same, right? So what is the current flowing in this case? Ignoring the channel length modulation, what will we have? We have, let us draw the small signal equivalent. So if you draw the small signal equivalent, you have a okay, let us not draw small signal because it is not asked small signal. It is a large signal because these voltages are given, right? So your gate voltage is 3.5 and in this case gate voltage is 1.5. In this case your source voltage is 0. In this case your source voltage is 1.5. So ID2 is equal to ID1. What is your ID2? Half mu n Cox W by W2 by L2 times VGS. What is your VGS? VGS is for Q2 is 3.5 minus 1.5, right? VGS minus VTH is 1.2 whole square is equal to half mu n Cox W1 by L1, and you will find out here 1.5 minus 0 minus 1.2 whole square. This you can cancel. L1 L2 same. So you have W2 by W1 is equal to, here you have 0.3 square. In this case you have how much? 2 minus 1.2, 0.8 square.
2 minus 1.2,
So
0.8
point,
square.
right? Is it okay?
0.8 square.
It is 0.8 square, right?
Yes sir.
This is W2, this is W1. W1 will come denominator. So this part will go
Yes
to
sir. Okay.
denominator.
Okay. Okay.
So it will W1 by W2, just reversing that will be 0.8 into zero point 0.8 over 0.3 into zero point 0.3. That will be 64 over 9. So 9 sevens are 63. So it will be around 63.1 something, 7.1 something. So W1 by W2 would be your, yeah, 7.11. Okay. So this is as far as this problem goes. I think I have left two problems earlier. So let me just solve this problem quickly. Okay. So understand first thing very carefully that this is a circuit where two MOSFETs are connected in parallel, okay? RD is 20 kilo ohm. Kn is this. Kn is half mu n Cox W by L. That is your 0.1 milliampere per volt square. Vt is equal to 0.8 volt. Okay. V2 is 0. That means this is grounded. And V1 is your 5 volt. So VGS is what? 0. That means VGS is 0 volt. VTH is 0.8 volt, right? So it is not, transistor is off. And in this case, VGS is 5 volt. VTH is 0.8 volt. So transistor is on. So my circuit is simplified to this connection. This connection, right? This is my V 5 volt and this is my V out. This is 5 volt and this is 20 kilo ohm. Okay. So now it is asked what is the output voltage V0 in large signal sense. Okay. So how will you find it out? First tell me, to find the output voltage, what will be the output voltage? Output voltage is nothing but your VDD minus IR times RD. This is your IR, let's say. So how will you assume that it is in saturation or in linear? Okay, check, right? Let me take it into saturation. So what will be my I? I will be what? Kn times VGS minus VTH whole square. So Kn is my 0.1 milliampere per volt square. And what is this? VGS minus VTH? 4.2 whole square, right?
Yes, sir.
So it will be around your 4.2 square into 0.1. So it will be 1.764 milliampere. So what is your V0 now? V0 is how much? 5 minus 20 times 1.764 milliampere, and kilo ohm will take care of that. So this into 20 minus 5. So it will be minus 30.28 volt. Okay. So this is your D terminal. So your VDS is minus 30.28 volt and your VGS minus VTH is 4.2 volt. So does it satisfy the saturation condition?
No, sir.
No, not correct. So what we'll do? We'll go to
Saturation
linear
equation.
region, right?
Linear region.
So in that region, what is my I? I is Kn times 2 VGS minus VTH times Vd is equal to my V0 minus V0 square. Why? Because Id is equal to mu n Cox W by L VGS minus VTH times VDS minus VDS square by 2. So this is how much? 2Kn. So that 2 is multiplied inside. So we'll get this. Okay. So what is my Kn? Kn is my 0.1. And let's say it will be in milliampere. And 2 times what will be VGS minus VTH? 4.8. This will be 2 times VGS minus VTH, and this will be V0 minus V0 square. Okay. And what about this current? So at page, So this is one equation, right? I is equal to 0.1 2 into 4.8 into V0 minus V0 square. This is
Sir,
I.
4.2 na? VGS 5, VT
Sorry. Yeah, right.
0.8,
4.2. Thank you. This is 4.2. And again, this current is the same thing which is flowing here. That will be 5 minus V0 over how much? 20. Right? So you have this equation 2 into 4.2 into V0 minus V0 square equals to 5 minus, and let's take this to 20 upwards, so it will be 2 and it will be 5 minus V0. So it is a quadratic equation. If you solve, V0 has to be positive. You will find out V0 will be your 0.29 volt. You can solve a quadratic equation, right? Minus B plus
Yes,
minus root over B square minus 4AC by 2A.
yes, sir.
Okay. So it will be 0.29 volt. So moving on to the last problem of today's session. In question 4, if V1 is 0 and V2 is 0.5, what will be the output voltage? That means if these two transistors are interchanged, it doesn't matter, right? Because it is a parallel combination. So output voltage will remain same. So it does not matter. V0 will remain 0.29 volt. Okay. So that is how you are going to solve the problems. So any query?
No, sir.
So let's end the session today here. So regarding the circuits, I'll request you to please practice the some examples. And if you need any PDF of the book, and if it is authorized, I will send you. Please drop me an email. I will send you the resource. Okay.
Yes, sir. Sir,
Okay.
your email ID ND, sir, once again.
No. It is dn6056@gmail.com. Okay.
Yes, sir.
Okay. So let's end the session today here.